morning. In today's class we will address the orbital requirements of satellites and therefore what a rocket should be doing. In the last class, just to refresh ourselves on what we learned, we told ourselves there are something like 8 planets revolving around the sun. We said these planets consisted of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. We also told ourselves there was one planet called Pluto, which is no longer considered to be a planet because it is not dense. Having said that, there is a lot of interest in exploring the different planets, and I will take 2 examples. The first example is one, or let us say this is again the repeat of what I just now told you. Maybe you have centrally the sun, which is shown in red there, you have about it maybe Mercury, after that maybe Venus, then Earth and the different planets. See, in between you also see some asteroids which we talked about in the last class. I will precisely come back to this point a little later, but having said that, we had a launch vehicle known as New Horizon launch. That means it is a rocket which goes and finds out what is happening in the Kuiper belt beyond Pluto. If you take the time taken to go to Pluto, this was launched in January 2006, it is supposed to reach there in another 4 or 5 years, something like it takes something like almost 10 years to reach Pluto. And what does it consist of? It consists of a series of rockets, one about the other, and the purpose of this course, at the end of this course, we should be able to size up a rocket, we must be able to put things in a rocket such that we can achieve a specific mission, and that is where I showed. And the next slide shows maybe something like a spacecraft which this particular rocket launches, and it goes round and round the planet what we are interested in. Therefore, this goes and looks at the Kuiper belt that is beyond Pluto. The next slide I show here a launch which took place some 3 days back. It was on August 5, 2011. It was an Atlas Centaur rocket, this again from US. It is supposed to have something known as a Juno mission, which is supposed to go and look at Jupiter. As per Greek mythology, I think we must have some general understanding. Jupiter is supposed to be a god and his wife is known as Juno, therefore they have named it as Juno mission, and again we will have to be able to find a rocket which will meet such missions, and that is what this course is all about. Having said that, in the last class we also looked at the different planets. We looked at the mass of the different planets, the diameter, the distance from the sun and so on. One thing we must keep in mind is the Earth's mass is around 5.974 into 10 to the power 24 kilograms, and its diameter is 12,756. The smallest planet is around Mercury, which is 1/3 the diameter of the Earth, and the largest we said was Jupiter, which is quite considerably big planet, right. Having said that, we also talked in terms of moons. We said that the Earth's moon is somewhat smaller than Mercury in size, and there are 31 moons which are available in solar system of the Milky Way galaxy. Having said that, we also talked in terms of atmosphere, because I asked a question, what is the difference between a rocket and an airplane or other vehicles? You all told me rocket is something which flies in vacuum. It is really not vacuum. Anything which goes in space is what we call as a rocket, and we talked in terms of the temperature variations above the surface of the Earth. The y axis here shows the altitude, the temperature is shown on the x axis. We told ourselves because the Earth gets heated by the sun, the layer of air above the Earth gets heated, and therefore the temperature drops from a high value of around 40 degrees centigrade at the surface of the Earth to a low value around minus 60 to 80 degrees centigrade at a height of around 10 kilometers, and at that height, that is the height around which an aeroplane flies. Maybe a jet aircraft flies at an altitude between 8 and 10 kilometers. Above this height, again the temperature drops, and the temperature increases. That means in the troposphere, just above the surface of the Earth, the temperature drops, and after some particular height between 10 and 15 kilometers, above that the temperature increases again. The increase is because the ozone gas which is available there absorbs the heat energy. But then you keep on going to higher and higher altitude, say around 50 kilometers. Beyond that, the amount of air available is very small, therefore there is nothing really to absorb the heat, and therefore the temperature begins to rise again. Whereas when you go to extremely high values around 80, 85 kilometers and so on, the individual atoms like oxygen atom combines with oxygen molecule to give out heat, and again the temperature increases. But then the pressure monotonically falls, and in thermosphere there is hardly any pressure. Therefore, the concept of temperature no longer holds good. It is the individual molecules which are at high temperature or which are moving at high velocity, whereas there is no continuum, we cannot even talk of temperature, it is a fictitious temperature. And therefore, when we talk of rockets, it goes through the troposphere, stratosphere, mesosphere into the thermosphere, and further is where a rocket flies. I think this must be clear to each one of us. Is there any confusion between, let us say, why the temperature decreases above the surface of the earth? The place where an aircraft flies is around 8 to 10 kilometers, where the temperature is around -45 to -50 degrees centigrade. Then you have the stratosphere, mesosphere, where the temperature again increases, and the temperature again decreases in the stratosphere. The temperature increases because of ozone. Ozone absorbs heat radiation. Mesosphere, not much gas there. In the thermosphere we have no continuum, and the individual atoms and molecules react to liberate heat, and you have something which is not continuum, we say molecular region, right. Is it clear, or is there any question here? Let us go ahead. What else did we do in the last class? We told ourselves, well, all planets move in elliptical paths and they trace out equal areas in equal time, and but if you see the newspapers and the science magazine over the last 2-3 months, they keep telling us the orbits are elliptical, but above the ellipse there are undulations which are there, and you see the green color shows the real orbit. But then there is something still more confusing. Even within the undulations there are further undulations like turbulence which is available. Therefore, if somebody is talking of turbulence, well, even the motion of the planets around the sun looks to be turbulent to me. But anyway, grossly it is all elliptical path, and we have Kepler. We talked in terms of Johannes Kepler in the last class. We told ourselves, what did Kepler tell? Well, there are 3 laws. One is all planets move in smooth elliptical orbit. The second, we said they trace equal areas in equal amount of time. In this figure, the sun is at one of the focus, and therefore you see the focus on the left hand side, around which those white patches show equal areas in equal time. And the third law, which was law of harmonics, we said that the time period t divided by r, namely t to the power 2 t squared divided by r cubed, is the same for all the 8 planets. Therefore, you have very well or synchronized motion of the planets around the sun, and therefore this is useful, or this was useful for Newton to be able to formulate the universal law for gravitation. How did we go to it? Before Newton, that means let us go back here. We told ourselves Johannes Kepler was in the period 1570 to 1630. Afterwards comes Galileo Galilei around the same time, little bit later, and what did he do? He was also interested in looking at the planets. You see him on the left hand side gazing at the planets, and he is supposed to have done an experiment in which a feather and a steel ball fall together in a place which is evacuated or vacuum, and he finds that the time taken is the same. And Newton did no experiments, he just relied on these observations. And what did Newton do? Well, he saw, it is stated that he sees an apple falling from a tree. He uses the information which Johannes Kepler gathered, namely you have elliptical motion, you have equal areas, you have t square by r cubed is a constant, and then he says, well, and there was this person Robert Hooke, you have all read about Hooke's law in mechanics, stress upon strain, and Hooke also was doing the same thing at precisely the same time, and Newton put everything together and he said, well, an apple gets attracted by the earth because earth is a large mass, just like the sun attracts the different planets. Therefore, he formulates the universal law for gravitational forces. Planets fall freely onto the sun, that means planets are freely falling bodies just like a stone falling on the earth. Therefore, what did we tell in the last class again? We said this states that if I have a heavy mass m1 as shown over here, and then I have a light mass m2 which is at a distance r away, then I have the attraction force with which the heavy body attracts the lighter body is given by F is equal to g into m1 m2 by r square. This is the universal law for gravitation. We said g has units of Newton meter square by kilogram square, the unit is 6.670 into 10 to the power minus 11. With this we should be able to do problems, but then we were not clear how this gravity force comes. What is this gravitational field? It comes from different areas from physics. We must be able to understand why gravitational field exists. It is still not proven, but you have very powerful minds like Stephen Hawking. We said he was a physicist who is looking into the different mechanisms. We had different people looking at the laws, but still not clear. We just told ourselves, if I stretch something, if I put a heavy mass, the heavy mass, and I put a light mass, the heavy mass maybe pulls down the stretched rubber, and therefore the light mass rolls towards it, and that is what we say is a field. And we went further, we expanded the value of the universal law g m1 m2 by r square in terms of, let us say, the heavy mass being the earth, r being the radius of the earth plus the altitude re plus h, and we found that F is equal to minus mg. And but the gravitational field is not constant all along the surface of the earth, because earth is little bit chubby in shape, it is not a pure sphere, and therefore you find that with the angle of inclination or the latitude and the height, the gravity or the acceleration due to gravity g keeps changing. Therefore we have F is equal to g m1 m2 by r square, or in the gravitational field of a particular planet, if g can be expressed in terms of, let us say, a unit, the unit comes out to be meter per second square, which people or all of us loosely call as acceleration due to gravity. There cannot be acceleration due to gravity, it is a field, therefore g is the field expressed in meter per second square. This is what we did in the last class. Let us progress further. Here I just expanded it out for our information. F is equal to g me, that is mass of the earth, radius of the earth re and h, and when we did this we found F is equal to minus mg, and we got the value of g as 9.8 meter per second square. This also we derived in the last class. Having said that, we have to keep something in mind. We defined what we called as inertial frame of reference. What did we say? All of us are moving, the earth is rotating, all the galaxies are moving, sun is also moving, therefore how do we define motion in space? This was a problem for us. Therefore we said either the object must be stationary, or I must be absolutely stationary, then I can see the motion of an object, or if I move at constant velocity, then the change in motion of the body is independent of my constant velocity. Therefore we define inertial frame of reference as a frame of reference which is either stationary or it moves at constant linear velocity. Therefore based on this linear frame of reference, we talk in terms of Newton's laws of motion, which is precisely what we have been talking all along, namely inertia. A body continues to remain in a state of rest or of uniform motion unless it is forced otherwise by an external force. Makes sense. We say the second law of Newton, we say rate of change of momentum is proportional to force, or force is equal to rate of change of momentum, F is equal to d by dt of mv. You expand it out, you take constant mass outside, you have d by dt of v, which is acceleration. Therefore we say the second law of Newton can be expressed either as between force and change of momentum, or between mass and acceleration, or we say acceleration from second law goes inversely as the mass of the body and directly as the force on a body. We will be using these laws, and the third law says that action and reaction are equal and opposite. But mind you, the important qualification is inertial frame of reference. These laws are valid only if the frame of reference is inertial, and this is important for all of us. Supposing I want to say I want to find out the temperature distribution in a rotor in a machine. Therefore I am looking at the blade is rotating. To be able to find the temperature of a blade, I will be sitting on the blade and monitoring the temperature, but I am rotating. That rotating body need not be an inertial frame of reference. Therefore, the momentum equation for a rotating body need not follow the Newton's laws. That means I will have another equation to describe it, and I come back to this. Let me just get into this last slide of what we did in the last class. We told ourselves, well, to be able to put anything in space, you need to give a force. Lucian, before the birth of Christ, around 40 AD or 40 BC I think, what he said is, a ship is there on the sea, there is a giant storm which pushes the ship into moon. He wanted to go to moon. But when we looked at Jules Verne, who was a popular science fiction author, he said, well, why not have a capsule which is contained in the barrel of a cannon and you push it through. But such things are not possible, as we shall see a little later. And therefore, the last part which we did in the class was, we talked in terms of asteroids which are there, which are loose bodies which are available in space, and one such asteroid missed the space station around 2 months back. Space station is a satellite which is in low earth orbit, and it is used for scientific experiments. And whenever they see some asteroids, they go and correct the position of the space station, slightly move it away such that the asteroid does not hit the satellite. And that is where you have these misses, these are all bodies in space which hit each other. But something which was disturbing and which we talked in the last class was, this I took from the Hindu, this came in February this year. It is said that on April 13, 2036, one asteroid, the name of the asteroid is Apophis, is supposed to hit the earth. And if this asteroid comes and hits the earth, well, it is reminiscent that the picture on the right side shows an asteroid hitting the earth, and the asteroid gets rapidly heated due to friction, it explodes and forms a blast wave, severe wind and extremely high temperatures. That might be the end of civilization itself. And in fact, it's told 6 million years ago the extinction of dinosaurs was because one asteroid came and hit the earth. Therefore, the question is, people have been always wondering how to make sure that if an asteroid is going to come and hit the earth, how do I deflect it? Therefore, one of the things which are talked of is, well, I have something like a heavy satellite which I put near to the asteroid, and now the asteroid has a certain mass, and I because of the force, the asteroid slightly shifts away, and I can shift it away from the earth, and this is known as a space tug. Maybe we will design a space tug in the next class. Having said that, I think this is all what we covered, and we set the pace to continue further. What did we say? In the frame of reference, which is inertial, I know the equations, I know Newton's law. But if I were to consider an orbiting, that shows the earth, something revolving around the earth as it were. The bottom picture shows the INSAT satellite going around the earth, it keeps on encircling the earth. You find these are all, that boy there, he throws a stone into orbit and it keeps on rotating round and round the earth. Now, what is the frame of reference here? The frame of reference may be, if I were to consider a particular, the pull of gravity attracts it and causes it to fall freely, while the forward orbital velocity component shifts it away from falling onto the earth, and the body gets into a circular orbit. Now, for me, the frame of reference cannot be, supposing I am standing here and looking at it, I see it going round and round. I find it difficult to describe that sphere. If I were to sit on the sphere, then I know I am here and I see everybody else going in some other motion. Therefore, I would like to get back and ask a question, can I get out of this inertial frame of reference and describe the motion around a rotating body? Let me put it this way. Let us take an example. All of us go to the circuses, and one of the things which is shown in a circus is, you have something like a spherical cage, a loosely cage. A motorcyclist gets in and he goes round and round it. All of us have seen it, right? How does he support himself? What is the principle by which he is on top? He does not fall down. And if I were to consider myself sitting along with the cyclist and I want to describe my motion, and that is how a satellite is there, I would like to know what is the type of forces which are acting on me, and for this to be able to correctly describe the motion of bodies as they are rotating, we say it is a non-inertial frame. It is not something which is moving at constant velocity or which is stationary, but in the frame of reference of something which is darkened there, I say well it is rotating, and that I call as x dot. I would like to be able to find out the forces, or rather describe the motion in the frame of reference of a rotating body. This is what I will be doing in today's class, and along with that we will be able to find out what we mean by orbit. Therefore, let us come back. I cease with the slideshow. Let us get back to the lecture. Therefore, what is it I am telling? I have something like an orbiting, something is orbiting over here, maybe I have the center over here. Let us say a ball is going round and round, this is the rotating frame of reference. I am interested in finding out the equation of motion with respect to the rotating frame of reference. Is there something more I have to do? My question is, as long as I considered myself to be stationary, I said inertial frame of reference is that Newton's laws of motion are okay, but if I move at constant velocity, the inertial frame of reference is there. What is the change when I use a rotating frame of reference? I want us to be very clear, because I think I must make myself absolutely clear on this. The perspective is not that I am standing here and we told ourselves when I stand on the earth I assume I am moving at constant velocity, then I am in an inertial frame of reference. I am not looking at the body from the inertial frame of reference, but I want to look at the body which I call as coordinate x dot, which is a rotational frame of reference. In other words, I also sit on this body and now I ask myself, can I describe my motion properly? Let me say, instead of me standing here and watching this mass go round, I tell myself, well, I am on this body and I want to describe my motion properly. In other words, you know that my motion around x, I am on this body, therefore with respect to the body my motion is dx by dt is equal to 0, right? There is no change. But how do I describe this motion? Let's come back. Let's say that I move with a velocity, angular velocity omega, and let's say at time t I am at this particular point, therefore the omega t is equal to theta. I start over here, at a time duration t I have reached this particular point, and therefore I can write this is my x coordinate, this is my y coordinate, this I call as x dot which I have just written excuse me. Therefore, I write now x prime is equal to, if the radius of the circle around which it is going is capital R, I can write x prime is equal to r cos omega t, this is x over here, y is equal to r sin omega t, right. That is, the x component of the radius is x cos theta and the y component of the radius is y r sin theta, and theta is equal to omega t. Therefore, I differentiate it, I get dx by dt is equal to minus r omega sin omega t, and I get dy by dt is equal to r, that is r omega into cos omega t. I further, instead of taking the velocity along x and along y, I want to find the acceleration along x and y. I get d2x by dt square is equal to minus, again it becomes minus omega square r, omega comes here, omega square r cos omega t, and the second equation I get is d2y by dt square is equal to minus omega square r into sin omega t. In other words, when a body is rotating, I find I can describe the acceleration along x. It is pointed, it is minus, it is in this direction, equal to minus omega square r cos omega t. I have acceleration in this direction is equal to minus omega square r sin omega t, and the net acceleration, if I were to write, I get the net acceleration A is equal to under root of these two, namely omega square r whole squared into sin square omega t plus cos square omega t, which is 1, and therefore this is equal to omega square r is the acceleration. That means when something is rotating, I have a net acceleration which is along the radius pointing towards O, because this is in this direction, this is in this direction, this is the direction in which it is rotating, and therefore I have a net acceleration over here. Now from second law we know that if something is rotating and I have an acceleration, I have for this particular body which is rotating, I have a force in this direction equal to minus m omega square. I did not take the value because I say that the force is in this direction towards the center, this is the body which is rotating, and therefore I have a force equal to mass into acceleration is equal to m omega square r. What is the name of this force? Cannot be centrifugal. It is a force which is acting. No, my question was what is this force? This force is known as centripetal force. This is all what we can say. We are considering a body which is rotating. I say that there is a net force which acts towards the center, and this force is equal to m omega square r. What is this point? I say I am sitting on this body in the perspective of this particular body, my x dot is 0. Therefore, when x dot is 0, dx prime by dt is equal to 0. Therefore, let us go back and write the equation here. We therefore know that d2 x bar by dt square is equal to 0, right. But then you find acceleration of the body in the frame of reference of the body is 0, but then I find, hey, I am talking of a force which is available to me. Therefore, if I have to describe my motion correctly, therefore let me put it, if I have to correctly sort of predict my motion, what should I do? It is necessary for me to put a force on the body equal to minus omega square r to be able to, in that case only this will be 0, because I find there is an acceleration which is coming, a force in this direction. For me to be stationary, I must put a force in this direction, and this is what I call, it cannot be real, right. I am putting a force on the body, therefore it is something which is virtual or which we call as a pseudo force. And why do I have to put this force? To be able to correctly describe the motion of the body when in the context of the body itself, because I am sitting on the body, and if I say that I am not moving, that is only possible when I put a motion like this such that the centripetal force and this pseudo force are same, and this pseudo force is what we call as centrifugal force. Let me just repeat whatever I have said in short. All what we are saying is, in an inertial frame of reference, Newton's laws are valid. Now I consider a frame of reference which is not an inertial frame, but it is a rotating frame. Now I am looking at the motion from the perspective of the body, which means I am sitting on the body. If I am sitting on the body and I am rotating, then in that case, to be able to correctly define my coordinate, or with respect to me if I want to define, it is necessary for me to be able to, I go round, I consider this, it is necessary for me to put a pseudo force to be able to correctly describe my body, because I find that d2, my position x dot by dt square is equal to 0. In other words, I have a centripetal force minus omega square r, and I have to put a force equal to plus m omega square r to be able to correctly determine my motion, which we call as a pseudo force. It is not a real force, but it helps me to find out the forces in a non inertial frame of reference. See, this we will keep on encountering whenever we use these codes, we use fluent code to determine some gas motion or gas mixture. We must be very clear, he might have written it for an inertial frame of reference. If I have a body which is sort of going on side, which is rotating, I could have some other forces. Therefore, frame of reference is extremely important in any problem what we consider. Therefore, now let me summarize what I have been telling you, so that we go back and start finding out what are the velocities in orbit and what we want to do. All what I have been telling is, well, I consider a body which is rotating, and I tell myself, if I am looking at the rotating frame of reference, it is necessary for me to put a pseudo force which I call as centrifugal force equal to m omega square into r, where m is the mass of the body. Therefore, let us come back to this problem. Let us consider Earth to be here. Let us consider a satellite or some body of mass m going around Earth as it were. Now I want to find out the motion of this particular body. Therefore, all what I say is, well, let it rotate with an angular velocity omega. Then the pseudo force is equal to pseudo force, which we call as centrifugal force, is equal to m omega square r, which is acting in this direction. Now what balances the pseudo force? What would be balancing? Let us say this object is going round the earth, what will be balancing this pseudo force? Gravity? How would you tell? What will you say? How would we describe it? You are telling me that the gravitational forces balance the pseudo force. In other words, all what I am saying is pseudo force acts in this direction equal to m omega square r, and what is the force in this direction? The gravitational force, which is given by universal law for gravitation, is equal to the mass of the body, mass of the earth, divided by r squared into the gravitational constant. Now we are saying some body is rotating around this, therefore I take the force balance, and what is the force balance? I have the pseudo force or centrifugal force m omega square r is equal to g into m mass of the earth divided by the distance from the center of the earth to this particular body, r square. And now I find out my angular velocity. M and m cancels, you find that irrespective of the mass of the body, the value of the angular velocity is the same, and I get is equal to g me by r cubed. And this is what gives us the angular velocity of rotation of a body around anything. If I were to consider, instead of the earth, I say I am going round the sun, say I go round the sun, and let us write the equation for it. we tell ourselves, well, I have the sun over here, I have a body going round the sun at a distance r from the center of the sun, this is my body of mass, let us say small m, this is the mass of the sun ms, the distance is r, then for exactly the same thing I have the gravity force, that is F is equal to mass of the sun into g into the mass of the body into r square, and I have the pseudo force here which is equal to excuse me m omega square r, right. Therefore, I get the angular velocity as equal to g mass of the planet into distance from the center of the planet. This could be a mission around moon, we have the angular velocity, and once I know the angular velocity I need the velocity of orbit, therefore the orbital velocity, what is the velocity with which it is rotating, v0, v0 is equal to what, r omega, which is equal to, I put the value of r here, and what is the value I get, r becomes r squared inside, that means I get r square over here into r cube, and therefore I get so many meters per second. This is how we calculate the orbital velocity of any body, like moon is going around the earth, you know the mass of the moon, you know the mass of the earth, you know the distance between the center of moon and center of earth, we know the speed at which the moon is travelling, which we call as orbital velocity. Let us do a simple example to illustrate this. Let us find out the velocity of a body, or let us say a spacecraft or something, which let us say we say this is the earth as it were, something is rotating around the earth at a height let us say of 100 kilometers above the earth. I want to find out the velocity of the orbit v0. Therefore, how do I just make use of this equation, I have v0 is equal to under root g, we said was equal to 6.670 10 to the power minus 11, what was the unit, Newton meter square by kilogram square, into the mass of the earth. The mass of the earth was 5.974 into 10 to the power 24 kg multiplied by kg divided by the r, you said 100 kilometers above the surface of the earth, therefore r is equal to, the radius of the earth is 6380 kilometers plus 100 kilometers, which is equal to 6480 kilometers into 10 to the power 3 meters, 1 over meter square, 1 over meter is meter, this is under root. Therefore, what am I left with? I am left with kilogram, kilogram, meter, Newton is equal to kilogram, meter per second square, therefore this becomes under root meter square by second square, and the unit is meter per second, so much meter per second is the orbital velocity, and this if you calculate will come out to be about 7.76 into 10 to the power 3 meter per second, or 7.76 kilometers per second. This is typically the velocity of a body orbiting the earth at a distance of 100, at a height of 100 kilometers. This is how we calculate the orbit velocity. Let us go a little bit further. What do we find from this? We find that as the height above the earth increases, the value of orbital velocity will keep coming down. When I reach infinite height, the orbital velocity is really 0, right. This is, in other words, whenever we are considering any planet, a body orbiting around the planet, I can calculate the velocity v0 in meters per second or the orbital velocity of the rotating body. We talk in terms of INSAT spacecraft which is going around the earth, and therefore we say, well, it is at this height and therefore it is rotating at this particular speed. Well, I think I'll stop here. In the next class, what we do is we will go into some details of, maybe, see, you find that the orbital velocity keeps falling. We would like to understand, but as the height of the body increases, I must give more velocity to the body to reach that height. Therefore, what is the total velocity which is required for a rotating body, and then we will go into some more details of different orbits and then fix what are the requirements for a rocket to be able to put some spacecraft in different orbits. That is what I want to do. Well, thank you then.